Yes, my name is Shiels. I work with a German company called H2Core Systems. We're a manufacturing integrator of hydrogen production systems based in Germany. Historically, H2Core is a spin-off from a family-run business in the hydraulic space, and we started getting into this hydrogen spectrum about maybe 4 years ago now. So since we started 4 years ago, we have probably built and shipped 200 of what we call hydrocabs. So these are systems that make hydrogen for a whole variety of purposes. And we've shipped those to about 40 countries. And we've basically done that within about the last 3 years. So even though I currently I get my laundry done in Jakarta, Indonesia, a lot of our activity is in Europe and in the US, who, let's say, had an earlier start in this whole hydrogen space. Sorry. So basically our main objective, obviously, is to remove dependence on fossil-based fuels and carbon-based fuels by using hydrogen. And the key word is green hydrogen, which requires two important elements. It requires water and access to renewables. If the renewables are green, then the hydrogen is called green. And that's really, the bottom line. When everybody asks you what is the cost of making hydrogen, the simple answer is it's whatever you pay for electricity. I need 53.3 kilowatt hours to make 1 kilogram of hydrogen. If you're buying that at 2 or 3 cents or 5 cents because you've implemented solar, then your cost to produce that on electricity alone is around about $4. But primarily it depends on the price you pay for electricity. Now our building block is this wonderful little box. It's about the size of a microwave oven. It's built by Enapter, and it's called an AEM electrolyzer. What's really cool about this little box is I think it will be in everybody's homes within the next 10 years. When people start putting solar panels on the roof or have access to renewable energy, that excess can be stored in your home, can be used to produce electricity, and we even experimented with using hydrogen for cooking. So if you come to our stand next door, I'll tell you how much hydrogen we need to boil to make pasta. And the results are quite interesting. But this module in its own right, if I give it 2.4 kilowatts of power, it will produce 500 liters of hydrogen in 1 hour, and that hydrogen is pre-compressed at 35 bar, which is a meaningful amount of energy to store it in a relatively, meaningful space without having to deal with compressors or high-pressure hydrogen or anything like that. So a lot of people, in terms of the user adoption of this type of technology, they really don't know what does 500 liters of hydrogen mean, right? What does it actually mean to me? And basically, 500 liters of hydrogen, it weighs 40 grams, it has a low heat value of 2 kilowatt hours. That would be enough to drive a fuel cell car for 10 kilometers. So when you think about it, I'm driving a fuel cell car with 10 liters of water. That's really what we're talking about here. The same hydrogen, if I run it through a fuel cell, will give me 1 kilowatt hour, which is enough to run my computer and lights for 24 hours or so. So everybody asks me, why do you use Enapter's AEM? And the simple answer is, we want to make systems. And we have discovered over our lifetime that the best place to make hydrogen is where it's going to be used. Making it centrally, distributing it is a very cost-effective, costly way of doing it, and it really limits the application usages for hydrogen. So I won't go into too much detail on the technologies because Sebastian covered that at a previous meeting, but everybody has heard about alkaline. It's been around for 100 years. It's the go-to industrial way to make hydrogen from electricity. It's got some downsides, which are, fall into areas such as the electrodes corrode very quickly, the concentration of electrolytes is very acidic, and you need to maintain a constant level of power, which isn't really very useful for renewables if your power is coming from renewables. The next technology is PEM. PEM has been around for nearly 20 years now. PEM is becoming very popular because PEM lends itself better if the variable energy going into the system is variable, like solar, wind, or whatever. But
PEM's got a couple of downsides from my perspective. And remember, my perspective is to put these where it's needed. So I want something simple and relatively uncomplicated. And PEM doesn't quite do that for me at the moment. So the difference with PEM and alkaline is I have a separator, separating the oxygen and the hydrogen, which come off the electrodes. But then I need a balancing plant to do the drying and the again further separation, because you can never completely separate that. All that balancing plant takes up space and adds to the cost. AEM, on the other hand, is very different. When AEM was developed, we thought of calling it PEM version 2, but really while it does cover both alkaline and PEM, AEM is very different in the way it works. And quite simply, how it works is water circulates on the anode side. It reacts with this catalyst, which is on this membrane, which is also a separator. The catalyst is Enapter secret sauce. The catalyst allows hydrogen from the water to pass through the membrane onto the cathode side. So there's no liquid circulating on the cathode side. Sometimes it's referred to as a dry cathode. The oxygen, we don't want it. We let it bubble off on the anode side. So the process or the way that works is actually very efficient. And from our aspect, we don't need to get involved with noble metals. The plates can be made using steel or aluminum. There's no rare earth material required. One of PEM's biggest problems is you need a lot of iridium. And to be honest, there isn't enough iridium on the planet to support the hydrogen production that everybody wants to get to in the world. So no iridium is a really big advantage, no platinum, no metals. One other advantage of, this is just a simulation showing how it works, but when you look at the balance of plant, inside that box, that microwave size on a power supply, a heater, and a pump. And that's it. Very, very simple. And because it's modular, it makes it easy to replace. Also, in terms of how it works, in the jungle when I'm using solar or whatever, I can run a module at 100%, or I can run it down to 60%. We used to be able to run it lower, but we capped it at 60%. So if I have a bunch of these modules together, I can run all of them at 100%, or one of them at 60%. That gives me great dynamic range, and I can react to it relatively real time as well. So we really take advantage of the modularity of the system. So depending on how much hydrogen somebody wants to make, or how much power is available, we basically put these in a cabinet, maximum 5 to a cabinet. That gives me 5 kilograms per day, or 2.5 kilometers per hour, and we can parallel these cabinets together to build up whatever capacity is required. So the analogy I like to use is, you guys are probably too young to remember mainframe computers, but in the old days, if you bought a computer from IBM or whatever, you had to buy the one they had, and you had to buy it big enough so it would last you for a long time. What killed mainframes was networking PCs. So the analogy here is the same. We're networking these electrolyzers together to build the scale that's actually required. So this is an example of our entry-level systems we make for people who want to start pilots because they want to get into understanding how hydrogen works. It can be a simple, one module in the cabinet with a dryer, a water tank module to 5 in the cabinet. And we do have many cases where we put a lot of these cabinets together. So if my pointer works. Anyway, the two middle configurations, the 100 kilowatt and the 200 kilowatt, are actually what we sell quite a lot of. And we sell those to companies who are planning to go into buying a 1 megawatt or 5 megawatt or 10 megawatt electrolyzer several years in the future. But we're giving them an opportunity to start now so they can work out about how to integrate this with their existing plants or their production, or how to manage the energy supply to these systems. Or, there's a lot of activity that happens around this system that's not quite obvious. And an easy way to learn is to start by something a tenth of the size, or a 20th of the size. And we can deliver these within about 3 months. That's the other big advantage. If you want to buy a 1 megawatt electrolyzer, megawatt electrolyzer, we have to wait 14 months generally. So we find that those two sizes in the middle seem to be very popular at the moment. Now, the analogy that I used about the networking PCs replacing mainframes, you can take that another stage further. So we don't network PCs anymore. Everything's in the cloud. So by the same inference, we take the stack out of the module, and we put the stack in strings, and we put those strings into a rack. We put that rack into a 40-foot container, and we centralize the balance plant on the roof usually. So the balance plant deals with the temperature, the heating, the water management, the drying process, etc. And we call that we used to call it the multi-core, it's now called the Nexus. And the Nexus is our 1 megawatt system. And that, I guess, we have probably, Enapter certainly have sold maybe 8 or 9 of these already. You can come and visit these, some of them which are already operational in various parts of Europe. The initial systems very much were first iterations of the product. We were very selective in terms of where they were sold. So, for example, we have several in Canada, several in Europe, several in Korea, several in China. But lead time-wise, again, we're not talking, very, very long lead times. Because of the modularity of the assembly and the manufacturing, we can generally produce these within, let's say, 8 to 12 months. Recently, we introduced sort of a halfway iteration between the stack version and the cabinet version. We call this Flex. And this product was really developed to suit a lot of requirements we were getting to use hydrogen for heating applications. So in many parts of the world, like even like Malaysia, there are manufacturing companies who use heat as part of the process, say, for example, making bricks or making ceramic tiles or whatever. So the idea was to have a smaller system, around 59 kilogram per day, 25 cubic meters per hour, that can be used either blended with natural gas or 100% hydrogen. And this is, it's skin-based because it has to go into a production-type environment. We launched this in November, and we have already sold 30 of these units. So H2Core is the company that's actually manufacturing these. We take the modules from Enapter, and we build the balance plant around it. So basically, we're in the business of making hydrogen production systems for a variety of applications. So obviously, we're very tied to the Enapter AEM module and the AEM electrolysis design and performance. And these go to a variety of different market segments. And, to be honest, Malaysia did play quite an important role in this development. The earlier systems that I was certainly involved with, the first one was in Thailand in 2014, but we deployed these systems as alternative to diesel generators for a lot of off-grid microgrids in Tapa, North Malaysia, in Sarawak, for a variety of different applications. So Malaysia was really the first place that we started combining the concept of make hydrogen, store it, and then use a fuel cell to basically to create power. And that application was really range extending batteries that were not being charged properly using solar PV. Now many of the requirements I'm getting are for industry, like feedstock. I want to make hydrogen and blend it with natural gas so I can claim I'm reducing my CO2 emissions. I have all the ammonia producers in Indonesia knocking my door down and want to know how much does an 80 megawatt system cost. But basically feedstock and blending, I think, is going to be the next sort of a big area of activity in Indonesia, in Malaysia, and certainly in Southeast Asia. So while we're on the topic of using an electrolyzer for something useful, like creating electricity, when it comes to creating electricity, we have to use a fuel cell. And the fuel cell operates almost in reverse to an electrolyzer. With an electrolyzer, I take electricity, and I take water,
fuel cell, I put in hydrogen, I get electricity, and I get water out. Unfortunately, I don't get the same water out as I put in, but basically it's opposite to how the electrolyzer works. Now, one of the interesting questions you might ask is, well, certainly let me say that PEM, proton exchange membrane, is not to be confused with PEM electrolyzer, but that is the most common type of fuel cell that you will hear. Now, there are other variants of that as well. I never mentioned SOFC, for example, but in terms of fuel cell, the parallel cell, PEM is probably one of the more common ones. So the question you might ask yourself is, these companies that make PEM fuel cells, why aren't they making electrolyzers? And I think you'll start to see that happening as well now. So I'm just going to skip through some examples of installations we have in Europe, and the parallel of what we're doing in Europe also has similar synergies in Asia, in Malaysia, in Indonesia, in the Philippines. So these are basically installations for companies, but they're being done in conjunction with colleges. And why is that? Well, the companies who are getting into hydrogen or testing for a variety of applications, they need the brains of young people to figure out how to optimize the system, how to develop, processes and procedures around it. So this is something I think would be very useful if it happened here. More collaboration with industry pulling in universities and not the other way around. We're not spending a university's budget here, we're spending commercial companies' budget, which means that the emphasis and the results that are expected are considerably higher. If ever I supply a system to a college, it either never gets used or they break it. So I'm much rather sell it for a purpose. So these are examples. The last slide was for an airport. We're making hydrogen to manage and run some of the airport vehicles, baggage trains and forklifts and stuff like that. THM is a company who need this as a way to provide fuel, if you like, for a fuel cell to act as a backup, because by law they have to have a diesel generator there with fuel to provide backup services. They don't really have much problem with the grid, but hydrogen is a more sort of useful way for them to do that. SBB Poland is a company that make lots and lots of stuff. They need hydrogen and as one of their feedstock items, but they also want hydrogen for a lot of their testing purposes, as well as customer backup. So these systems were all deployed in the last, say, 2 years, and the reasons why they were deployed and the knowledge we picked up from the understanding why the companies wanted to do it and how their systems worked has been quite invaluable to us as an integrator. This is a really interesting project in the States. It's basically a system that this company, Lancia, they're in the business of low dumping. So they get a phone call from the Texas power grid saying, I need you to produce 20 megawatts. And if they say yes, they have to do it in 16 seconds. So for them, it's free electricity. So thanks to the US IRA program, if they make 1 kilogram of green hydrogen, the government will pay them $3. So for them, it's a no-brainer. All our electrolyzer has to do, all the Enapter electrolyzer has to do is to go from 0 to hero in less than 16 seconds. To take that load that quickly. This is something that I think is going to become an interesting, further development from the grids, for the load balancing for grids, load dumping for grids. So these are some more examples. I'll just quickly cycle through them for the minutes of time. But some of the more interesting projects which have a very strong parallel to what we do in Asia are these containerized power systems. So this company in the States, they make a 20-foot container, 40-foot container, and it gets dropped into, say, if the WHO are doing a food program for refugees, whatever, they need power in a hurry, they put in solar, they put in this container, and that provides power for the food supplier for medical aid type systems. And also in another company in the US, you have a trailer-based version for disaster relief services. So in America, if you have a disaster, everything's out for a week. So you need to be able to provide communications, control, medical services And you can only get there usually by your Ford F-150 towing a trailer, and they build systems around that. And again, hydrogen is used to range extend the batteries that are being charged by solar. The big difference, because the target is the military and the target is emergency services, the gas, hydrogen is stored in metal hydride, not in investments. So basically, if we sort of look at the scale of applications here, I guess our earliest baptism of fire was doing microgrids in Malaysia, and the requirement from the various power companies, for want of a better word, was that if I'm in the camp home, I give each house 3 kilowatt hours of electricity, 1 kilowatt peak, and that's what you have to maintain. Yeah? But for the way they used to do it in the old days was they put in solar, they put in batteries, they oversized the solar, they hugely oversized the batteries, and then you needed a gigantic diesel generator to charge the batteries and to carry the load. Our approach, which I'll explain in more detail, is certainly radically different. So if I was to sort of break down where I see the opportunity space in markets like Indonesia, for example, I certainly think probably let's call it the low-hanging fruit are definitely remote grids that are commonly served by what we call an island power system. So in Indonesia, PLN, for example, they might put in a 300-400 kVA diesel generator or a pair of them, and that's how they power the town or the village. And their biggest problem is the cost of delivering fuel to that site. So for me, that's the low-hanging fruit. In terms of something we can do straight away, and something that doesn't cost them that much to do either. Yeah? The next area of interest appears to be this gas blending. So we're in discussions with the Department of Environment in Singapore, for example, who manage all the crematoriums. So you die in Singapore, you generally get cremated. What do they use? Natural gas. For me, it's a sales guy's dream. One door, they got money, they got KPIs. So let's help them reduce their emissions by blending hydrogen for their crematoriums. But that's just a crazy left extreme example. Other than that, again, there are people who need hydrogen, and they either need hydrogen because it's a raw material in part of the product they make. Now, we won't go down steel and glass for a moment because their appetite for hydrogen is enormous. But certainly, e-fuels, ammonia, methanol, they all need hydrogen as a feedstock. There are some applications that need hydrogen because it's a consumable. So, for example, a number of power stations who have gas turbines, they use hydrogen to cool the turbines. Their system is meant to be a closed loop, but because hydrogen leaks all the time, they have to actually replace it with fresh hydrogen because it leaks all the time. So that's another application that we have done some work on now. And I think one of the other emerging areas is going to be, let's say, curtailment requirements for when people start putting out renewables, you will have an excess of renewable energy and it is nowhere to go. And this idea of being able to convert it into hydrogen for long-term storage becomes quite attractive. And I'm looking at my clock here and I have 3 minutes left. So we make basically off-the-shelf solutions. We work only with integrators. We don't want to sell directly to particular customers. We'd rather have local partners or what we call integrators deal with that. We just make and design the system at the back end. And in terms of projects, our biggest problem is that with the greatest will in the world, yes, there are incentives in Europe and the US, but let's be real, the only green people care about in this part of the world has got Benjamin Franklin's face in the front. It has to make sense. And that's where the challenge lies. So there are potential projects, and they're either feel-good projects or they're forced by the government. The Indonesian government might say, I've been to Bali, I've just been beaten up by the World Forum because I have to reduce my emissions. We need to do something. We need to be seen to do something about it. But the projects that we like to do are ones that actually provide a better value to the customer. So by implementing this technology, we should be able to provide a higher service reliability, we should be able to overall CapEx, OpEx show a lower total cost of ownership over that period of time. And more importantly, we're giving the user independence from head office or from the capital city. So to do that, we have to be experts in going in and analysing existing OpEx and CapEx. The actual OpEx is the important number. Everybody looks at the cost of fuel cells and they don't look at what the OpEx is and what they're currently spending. And that can be a really big deciding factor. Yes, we may have a higher CapEx than if I'm being replaced by a diesel generator, but if I add the operating costs, which are extremely low compared to diesel generators, those lines will end up crossing very quickly. So for me, I think that the sweet spot for countries like Indonesia, certainly, is addressing the renewable challenge. So on many cases where we see installations of solar plus battery, there are times of the day when you're generating energy and it's got nowhere to go. And the reason for that is when you design your solar system, you design it for the worst season of the year, because you have to provide power during the rainy season, for example. So during the better time of the year, you're producing energy, which generally has nowhere to go because the energy is produced during the day, everybody's out of their homes doing work or whatever, and that's really what we want to harvest and turn into hydrogen. By doing that, we don't need another backup system, and we have basically free fuel for effectively life. So I would call that solution a hydrogen battery, because we're acting as a battery to a battery, for want of a better word, but basically there's an element of software involved and also an element of AI where we can optimize when to make the hydrogen. So on the previous graph, it looked like the only opportunity was at the end of the day. Once we know the weather, and we know the season variations, and we know the load profile and how people do things, tomorrow's a public holiday, very different than today, we can optimize that opportunity space to make hydrogen. So, for example, this is a solution that provides many utility companies who have to provide power to a remote place because of CSR responsibilities, not because they pay their bills. They won't pay their bills, but because it's part of their CSR responsibilities. So, the solution in their eyes, we can guarantee the cost per kilowatt hour. This system will operate for a minimum of 10 years without any major parts replacement. And overall, CapEx OpEx is cheaper than what we currently can position at the moment. So just as a very extreme example, I can't use an example of Indonesia because it's under discussion at the moment, but this is an example in Kenya that we worked on that we got approval for. So this is an island in Lake Victoria called Phi Island, serviced by this useless 300 kVA genset that spends most of its time not working. But look at the cost of fuel, delivered fuel to that site. It started off at around €12,000 in January, and by the time December of 2023, we were paying close to 30k euro now. So this island, there are 10,000 people living there, so what interests me is what benefit we can bring to that island by providing reliable, scalable power. And the simple answer was they fish in that lake, and that fish is considered a galaxy in Nairobi, but Nairobi is 700 kilometers away, so power would enable industries like food processing and other type of activities to take place. But the basic solution that we designed for them is basically done this way. You give me your fuel money, you give me your existing OpEx cost, and I will turn that money and use it to finance CapEx. When my cost is paid for, I will hand the system over to you. Those are the opportunities that we are ideally looking for, and those are what I think is the low-hanging fruit in markets like Indonesia. So, nearly there. So, in a way to educate people and to open up the spectrum and allow companies to come in and learn more, we have worked with Enapter have developed a learning centre in Bangkok, and we have the Phi Suea House project in Chang Mai. Either of those places are available to come and visit. Just give us a call anytime. Chang Mai is interesting because it's probably Asia, maybe the world's first completely off-grid green hydrogen renewable energy storage system. The EGAT Learning Centre, basically EGAT are a big gas company, they're getting into this hydrogen space quite quite deeply. They built a house in the car park, they call it the hydrogen house, and it's mainly used to help businesses, who want to get into hydrogen for their own purposes, learn and understand more how to actually do that. Now, I have to talk about Indonesia. So this came from Indonesia's global hydrogen hub, Desire. Does it look familiar? Looks exactly like Malaysia's, right? What we saw earlier today. Almost exactly the same. So Indonesia is struggling with what to do in this space. Like many countries, they're trying to balance the fact that they produce oil, they don't have that much gas, they have to reduce their emissions, but more importantly, in Indonesia, they have to subsidize the fuel that goes into the pump, into the car. So if I can replace the diesel generator, I'll save them the fuel subsidy money in addition to the existing OPEX as well. But from Indonesia's perspective, what they're looking at, like the Philippines, like Malaysia, is they have an awful large potential to produce renewable energy. In Indonesia's case, yes, solar, yes, some wind, but not huge wind. Geothermal, definitely. Hydro, most definitely. Floating solar and hydro, absolutely, but most definitely. In terms of the potential capacity, if I was to translate that into hydrogen, it looks enormous. But getting there is the challenge. And what are they doing about getting there? Well, studies, roadmaps, feasibility studies, committees. That's the level they are at the moment, right? And again, from my perspective, if you look at, say, the pilot projects they're looking at doing, they're focusing a lot on transport, which I don't think is necessarily a good idea. I'm a big fan of replacing the diesel generator. Start with that. You do your buses, your cars will take time because there's more. It's not a simple case of replacing a car with a hydrogen car. You need infrastructure. But we don't need that if I'm replacing a diesel generator because I'm just making hydrogen on site where it's needed, getting rid of that diesel generator. That's really where we want to go. Yeah? So, last one, we're okay. Last one. So, it's a no-brainer. You won't be able to drive a car in London in another 5 or 6 years. The same with most cities around the world. Fuel cells are inevitable. That means hydrogen is inevitable, and making it where it's needed, to me, makes most practical sense. So we're looking for any opportunities where I can take out an existing diesel generator. And to do that is something that we can do very easily, very, very effectively. Yeah? So thank you for your time. And I'd like to say, jump on, yeah?